Hey everyone! Have you ever wondered why your phone battery gets warm when you're charging it or why your car engine heats up when you're driving? You guessed it, these are perfect examples of energy being transferred in different forms. Welcome to the first law of thermodynamics, or what I like to call the law of energy conservation. The first law tells us that energy can neither be created nor destroyed, but it can only be transferred or converted from one form to another. That means the total amount of energy in a system stays the same. So, when we talk about the internal energy of a system, it's the sum of all the microscopic kinetic and potential energies of its particles. And here's the key part: the energy added as heat, Q, and the energy used to do work, W, are the two major ways that energy enters and exits a system. The first law is written as delta U equals Q minus W, where delta U is the change in internal energy, Q is the heat added to the system, and W is the work done by the system. Now, let's break down the two major components of this equation, heat and work. Heat is energy that flows due to a temperature difference, like when you place a cold spoon in a hot cup of coffee and the spoon gets warmer. Work, on the other hand, is energy transferred when a force causes a displacement. For example, when a gas in a piston expands and pushes against the walls, it's doing work. The work done by the system can be expressed as W equals to P times delta V, where P is the pressure and delta V is the change in volume. So, if gas expands, work is done and energy is transferred. This is why, in thermodynamics, work and heat are not the same, they both transfer energy but in different ways. Let's dive deeper into internal energy. Imagine you're boiling water. The water molecules are moving faster, and that's because the system's internal energy is increasing. It's the total energy stored inside the system coming from the motion of molecules and their interactions. For an ideal gas, the internal energy depends only on temperature and is given by U equals 3/2 times N into R into T, where N is the number of moles of gas, R is the gas constant, and T is the temperature in Kelvin. So as you heat a gas, its internal energy increases because the molecules are moving faster. In thermodynamics, internal energy is not just the temperature, it's the entire system's energy. So, how does the first law come into play in real-life systems? Picture a heat engine. It takes in heat, Q, does work, W, by moving parts, and expels some heat as waste. This is exactly how a car engine works. The energy from fuel is converted into work, moving the car, but some energy is lost as heat in the exhaust. The first law ensures energy conservation. The work done by the engine comes from the heat absorbed, and the difference in energy is stored in the system's internal energy. It's like a money system. The heat you add is like income, the work done is like expenses, and the internal energy is your savings. Let's see the first law in action with an example. Suppose we have a gas in a piston. The gas is heated and 500 joules of heat is added to the system. The gas does 200 joules of work. We want to find out the change in the system's internal energy. Here's the first law in action. Delta U equals Q minus W. Now, let's substitute the values. Delta U equals 500 joules, heat added, minus 200 joules, work done. So, delta U equals 300 joules. The internal energy increases by 300 joules. This shows us how heat and work influence the system's energy. The work done by the gas took some energy away, but the rest was added as heat, increasing the internal energy. Alright, let's wrap it up. The first law of thermodynamics tells us that energy is never lost, it's simply transferred or converted. Heat and work are the two key ways energy moves in and out of systems, And internal energy is the total energy stored in a system. Whether we are heating up a gas or running a car engine, this law governs all energy exchanges. So next time you heat your coffee or fuel your car, remember, the first law is keeping track of all that energy flow. I hope this clears up how heat, work, and internal energy are all connected. See you in the next session where we'll explore more fascinating physics concepts.